Hello, everybody. Welcome to the course. I hope that you can hear me. Please let me know.
Yes, Professor, your voice is clear.
All right, thank you. So, last class we saw together some basic principle on thermocouples. Once again, the thermocouple is a transducer that is capable to measure the temperature from the output tension of a thermocouple itself. That is a device composed by two elements at two junctions. One junction is placed at a cold temperature, so cold temperature, and the other one is placed at a hot temperature, that is the unknown one. So the idea is that once we know the temperature of the cold junction, the cold temperature, then we can estimate the temperature of the hot junction just by evaluating the output tension, refer that output tension to the 0 degrees Celsius temperature, and then therefore we have to apply the law of the intermediate temperature, and then always using tables, we can find out the temperature corresponding to the output tension when referring to a thermocouple, equivalent thermocouple that is located, that is having the cold junction at the 0 degree Celsius. Now, we also end the class, Tuesday's class, when referring to what we call a base circuit, okay? That is what I call base circuit, measuring circuit. And in this base circuit, for example, we can have something related to a steel alloy. Then we have Costantana for the second material. Okay, for the second material. And this thermocouple is so that we are having the hot temperature to, for example, corresponding to a wall temperature whose unknown, for example, is T. Okay, and then we can use a measuring device like a voltmeter to see what is the output tension at the other end of the thermocouple. But as you can see here, the most important thing that we have to consider, beside the hot junction, of course, is that we have to be sure that these two electrical terminals are at the same temperature, and we have to know such a temperature. Okay, so we have two specific attention doing that. First, these two electrical terminals must be at the same temperature, so no temperature gradient, because the law of the intermediate temperature will tell us that we will have a bias of the output tension. And we have to know this temperature so that we can have a reference to our table in order to obtain the unknown temperature T at the wall side. Okay. However, this base circuit, although very clear and hopefully and simple in its usage, is not that cheap. I mean, if you are referring to whatever thermocouple, the materials generally used for the thermocouple are not that cheap. So they have a lot of cost if we consider a very long cable, connecting cable. So when we're referring to a practical measuring circuit for long cable that are using long cables, then we have to change a little bit that layout, and therefore what we got is something that now I'm going to draw. So once again, we have the wall temperature. That is the one we would like to know. Then we have the junction here, the wall side, the hot junction. But now what we are having is that we are considering, let's say, a change of the wirings. Okay, remember we had here the steel alloy base wiring, then we have the Costantana here.
Professore, mi scusi, sta registrando?
No! Bravo che me l'ha detto. Vediamo. The recording should start shortly. Can you see the screen?
Sì,
Okay. Still waiting for the recording.
professore, se la registrazione non parte, volendo potrei anche provare a registrare io lo schermo e poi a metterlo nella cartella condivisa. Se non dovesse
Potrebbe essere un'alternativa. Adesso aspetta un attimo, fammi vedere che succede. Perché lui parte e poi non so cosa
Ecco, è
accade.
partito adesso. È
Partito?
partito? Sì, dice che sta partendo.
Però ancora non, non mi dà l'ok. Ok. Okay, so in order to avoid the costs associated to the base circuit, because the cost of the wirings or the typical thermocouple are not that cheap, then we move to a different layout that is a little bit more complicated because of a connection. This connection is like this one, so the starting point is still the same. We are having the thermocouple, same materials, steel and Costantana. Then we have a junction. Let me call this junction as Q1 and Q2, corresponding to the two electrical connectors. And then, for example, we are having a different material like this, copper, for example, that is cheaper than the other ones. And these copper material wirings are directly entering your measuring circuit, your voltmeter, as we already had before. Okay, so we are having the same screen as we already had. Now it's just fine. Okay. Why doing that? Because this layout is cheaper than the basic layout. So let me use a different color. This, let's say, practical circuit is cheaper than the base one. Okay, however, once again, we have to be sure that at the joint, at the connection here, when we are having the connectors Q1 and Q2 that are, let's say, at a temperature T2, we have to be sure that both, please note, just a remark, that both Q1 and Q2 must be at the same temperature, T2, and T2 must be known with precision, let's say that. Okay, so it is cheaper for sure, this kind of circuit. It is the practical one that we can have, but however, care should be taken because of the connection. Temperature must satisfy the fact that the two connectors, electrical connectors, should be at the same temperature, and we have to know the temperature T2. Once we know that, of course, then we can use tables, and then for the output tension, we can derive the output tension of the same thermocouple that is placed at the cold temperature equal to 0, and then from tables we can estimate the temperature as we already did. Okay, the industrial layout is starting from this one, but with a slight difference once again. So the industrial circuit, measuring circuit, let's say circuit, is similar to the previous one. I'm going to redraw that once again. Starting point the same. Okay, we have the connection because we don't want to have costly measuring circuit. Then, for example, we use copper cabling wiring, sorry. As we already have, okay. But now we introduce a sort of controller here in the shape of a thermistor or whatever resistive based thermometer. Okay, let me call that R. Okay, that is capable to sense the temperature, and then this information goes straight to a compensating circuit like this. Okay, that just start from the information of the actual temperature of the connection R3, sorry, R, okay, corresponding to, let's say, the temperature T2, okay, and then provides the correct or the compensated calibrated output, okay, that could be directly used, okay, into your, let's say, voltmeter as you already have, okay. Okay. So in this industrial circuit, what we got is a compensating circuit. This compensating circuit uses, of course, an additional transducer, for example, a resistive-based thermometer, the one that I show you in the connection between the copper and the other material. Remember, we had once again the steel alloy cable and the Costantana alloy cable. And at that intersection, when we change the material, we have to perfectly know the temperature as the practical one, but for the industrial circuit, what we got is a compensating circuit that reads this kind of temperature and introduce a compensating potential, and therefore the output from the voltmeter should give you directly the information that there is not any influence by from the connection from T2. Okay, and therefore then we can use table as we already have. The advantage of this is that we don't have to measure the temperature T2 at the connection point because it is done automatically by the compensating circuit. And of course, this is much more practically for industrial purposes. Okay, the last circuit is, let's say, the laboratory one, the one that is very useful for very precise measurements. Okay, so let me call that laboratory measurements. Okay, and that is not practically at all. We are not going to use that, but if you would like to have that very precise measure, then you can refer to this layout. So what we got is the wall temperature. Once again, our hot junction here, same materials as before. So we have steel base material 1, then we have Costantana material 2. And then what happens is that we use the melting ice as the reference, so the intermediate material. Okay, so what we got here, let me draw a Dewar container like this. In order not to have any heat exchange from the outside to the inside of this container. Okay, inside the container we are having water. Let me specify that in order to increase the accuracy, it is a distilled water, and inside this water there are some ice cubes, okay, like this, just to replicate the just to replicate the melting. That is the most important thing. Melting ice, sorry, water. Melting ice condition, that means that we are at 0 degree Celsius for sure. So by using that additional device, what we are doing is that just use this, then go down, and then we are having another junction here. The same for the Costantana, we are having another junction, and then we can exit, for example, using whatever material like copper, as we already have. And then we enter your voltmeter. Okay, nothing special more. Okay, so by using this layout that I call laboratory, useful for laboratory measurement, what we are sure is that the junction between the basic thermocouple and the other one that allows me to have a long connection, for example, okay, and cheaper one, is happening at a very well-known temperature, and this temperature is 0 degrees, so that we have to just to compare the output tension with the tables and have the final result, which is much easier. Okay, what are the issues of thermocouples in general, regardless the type of the measuring circuit, the type of layout? The most important thing is aging. So the major issue is aging. Okay, so what we need is, after a certain operative life, a recalibration is required. Or simply replacement, if that is not more behaving as the actual behavior, okay, as the expected behavior. Okay, a last information is concerning the type of thermocouples. we saw thermocouples type J, T, S that are operating in the temperature range that I gave you last Tuesday. Okay. When you are facing with very high temperature, you can also refer to 3 other thermocouples that are very important for high temperature. So for T very high, okay, then you can refer to the rhodium iridium thermocouple. Okay, for which the maximum operating range temperature is 2020 100 degrees Celsius. Of course, sensitivity is low, about 6 microvolts per degree Celsius. The other thermocouple is tungsten and rhenium. It goes a little bit higher, 2700 degrees Celsius. Okay, sensitivity the same as before, 6 microvolt per Celsius. And the third one is boron graphite. It goes up to, once again, 2700 degrees Celsius. Sensitivity is higher. Okay, so this is the overall choice that you can have when referring to very high temperature when using such a transducer, such a thermocouple. Okay, so let's end our analysis of such a transducer for the measurement of temperature, thermocouples. So remember the basic principle, the Seebeck effect that could be reviewed as a Peltier and Thomson. Then the two laws that we saw together, intermediate material and successive temperatures. Then we can see also how this, we saw also how this thermocouple work. That is, we need to have some references corresponding to the cold temperature that is 0 degree by default. If not, and that is what's happening in general, you have to use the intermediate temperature law in order to have that. And then some basic circuits for the measurement. The basic one, practical one, industrial, and then for the laboratory. Now, let's change the transducer type. Let's see what's happening when we are in need of measuring another physical quantity that is very important for structural analysis, that is the acceleration. Okay, so let's start together and see how an accelerometer is working. There are different type of accelerometers. What we will see together is the piezoelectric base accelerometer. Okay, so let me call that PZT, piezoelectric. Base accelerometer. And we already introduced the PZT materials, the PZT property of such materials. And what we got is that when we are in a condition that there is an excitation, okay, that is acting on a PZT material, then what's happening is that there are electrical charges as the final effect. Okay, so what we can see is that these electrical charges are, let's say, proportional to the excitation. Okay, now if we consider a generic PZT material, what we can say is that, for example, if we are referring to such a layout in which your PZT material is a sort of prismatic element in a reference frame, for example, like this, but it doesn't matter, it's just for having some ideas. Okay, like this. So let's say X, Y, Z. We have the material that is having a dimension that is H. Then, if we are exciting, for example, with an external loading, that is a force F in some phases, for example, the one that I draw, then it could happen that there is an electrical charge, for example, negative at the upper phase and positive at the lower phase of this PZT crystal. Okay, these are electrical charges. Okay, positive and negative according to the different position that they got in the material. And of course, the plane, the surface in which those charges are collected depends on the type of the PZT materials and depends on the direction of the external force. So what we can say is that the charge Q that is collecting on a surface whose normal is in the direction I could be related generally to your force that is acting in another direction J and by the EJ that is your piezoelectric constant. Okay. By the way, the value, the ordinal value of this constant is 10 to negative 12 Coulomb over Newton, okay? Just to give you a reference in numbers. What happens? Now, that is the piezoelectric material. Now, what we can say is that those charges, those electrical charges, are kept separated by an electrical dielectric. Okay, and this electrical dielectric is just the piezoelectric material itself, the piezoelectric crystal. Okay, so what we can say is that the electrical charges are kept away from each other by the dielectric. That is just the PZT crystal, the one that I considered before. Okay, therefore, because of this, we can review such a core behavior of the accelerometer as a capacitor, an electrical capacitor. Okay,